Hi everyone. Let's see. We'll give it a minute or so for people to join. Yep, that looks good. Okay, let's get started. Thanks for joining the ASC Flux from Space webinar series. Today we have Mark Bourassa from FSU. Title of the talk is on the screen. Mark, take it away. Thank you.
Thank you. And this time the weather's good, so it should work. This is work that was done by a graduate student, Danny Wallace, under the supervision of myself and Heather Hobach. We'll be talking about using log profile analyses of dropsonde data in hurricane conditions to estimate fluxes under hurricanes. So first part of the talk will be a review of dropsonde data, since most people probably aren't terribly familiar with it. And then we'll go over the methodology for getting that 10-meter wind. And this is presented not as more as a proof of concept and as a final work, but it does work. And then for remote sensing, we want to have this information so we have something to calibrate to. We want to know what we're actually measuring and tune to it. And the problem under hurricanes is that the definition of a 10-meter wind is still your full definition, but it's different than what most people use. And I'll go over those differences and some of the implications. Then, as a result of doing this, it turns out we can get RC fluxes. So I'll show those. Again, this work is in review, and I want to thank Ralph Foster for some really valuable input in keeping us doing the full solution with stability included. Ralph has been a huge part of that. So Dropsondes. These are global positioning system data for tracking the position. As it moves, position moves, you can estimate the speed. These are tubes that are dropped out of an aircraft. Eventually a parachute emerges. There's a cord holding it, and they fall rather rapidly through the atmosphere, gathering data. So it's a fairly straightforward system. It's been around for a while, and this is the kind of tube that it gets launched out of in the floor of an aircraft. You slip the tube in, close it, and launch. This is an example of the data you'd get from it. Here's pressure on this axis, wind speed on the bottom axis. In this case, we use data that are processed through Aspen. It's an automatically QCing system. The data in Aspen are in yellow, and they are noticeably different than the unmodified data. There are one difference is that Aspen corrects for changes in height as the instrument falls. So if you don't use that correction, you get a different looking profile than you would with the raw data. It's also fairly noisy. I'll talk about that in a bit. And then at these lower wind speeds for the more extreme conditions, we tend to not see what we'd expect. Theory suggests that you get a profile that increases, a wind profile that increases as you go up in height with the logarithm of height. And, that's not what we're seeing here. There's a lot of cases like this. You see the same thing from remotely sensed observations from aircraft with IRAP. And if you took the 10-meter winds, the winds 10 meters above the ground, I should say, above the water surface, then you would get a much higher wind speed than you might otherwise get. I'll show you why as we go on. One other point to make on these, this looks like it's noisy. Ralph Foster has shown that a lot of the back and forth perturbations in wind speeds are proportional to changes in humidity. And that suggests that they're related to turbulence rather than just noise, which is important. So we're going to assume that Monin-Obukov similarity theory applies. So you're going to get a layer that's roughly logarithmic with some caveats that go into a more complicated theory. So you have this near surface log layer. Below it, and often much closer to the surface than indicated here, is a roughness layer. This is where the air flows around waves. And it's the log profiles don't apply in this layer. You don't want to take data from here to solve for physics here, or you get bad results. Similarly, above the log layer is an Ekman layer, and if we take data from there to solve physics for here, it's bad. So part of what we have to do is identify this log layer from the dropsonde data. Now, in the case of we'll use the Aspen data, and we're assuming that as they fall, they sample enough different conditions that you get a reasonable representation of a mean. This is not something that you would probably take for truth without checking. We've checked. It works better than I would have hoped. For higher wind speeds, there's a very decent signal to noise ratio. For more moderate wind speeds, it's not as effective, and I'll go into some of that later. But we find that you can find these log layers in a single profile. You don't need to combine the data from many profiles to get a log layer, as is typically done in studies using dropsondes. And then also we find in that layer down here that there's quite often sprays or what appears to be a gust, but it's often a spray layer at higher wind speeds. So I'll talk a little bit more about the spray layer later. So what are we looking at physically or mathematically in solving? We have a log wind profile. So U is wind speed. I indicates the height of the observation layer. So you just usually stack these up from the bottom of the layer being I equals 0 to the top of the layer that you're working with being the maximum value of I. And there's a corresponding height with that. And we see that the wind speed changes roughly logarithmically with height. But we have to take into account a surface current. Originally, we assumed that the surface values were what we got from the sonde for humidity and temperature, which I'll talk about in a bit. And for wind, we assumed 0. It turns out this didn't work very well. And we were better off solving for a surface velocity. They're not large, but the solutions are sensitive to it, and we could do it. So we did it. This is a constant. This is related to all the fluxes. It's proportional to the wind profile, so the bigger this value is, the stronger the winds are, the stronger the stress is. This is a friction velocity. We then have a roughness length, so this would be kind of a scale for cranking up the wind speed. This is a scale for the curvature of the wind speed with height. And then this D is a displacement height. Well, technically it's displacement height minus a roughness length, but the roughness length is so tiny compared to this displacement height that it's the same thing practically. And this is a vertical offset of the log profile. So if you think of flow over trees, it almost makes more sense than thinking about it over waves, because you know the profile is going to extrapolate to 0 somewhere around the top of the trees, and the profile is pushed up by the height of the trees. Okay, over waves that happens too, except it doesn't get pushed up as much. You can measure this in wave tanks. It's clearly non-zero, but it's not big normally. On hurricanes, it gets bigger. And then this is a stability term that accounts for the vertical stratification of the atmosphere. So it's a dynamic stratification term. If it's unstable, there's more mixing. If it's stable, there's less mixing. And it changes the shape of this profile. It causes a deviation from the straight profile you'd expect if this term was 0. And really, this should be Z minus D to get a log profile. Accounting for D causes a switch of this profile at the low end away from here, and so does the stability correction. So those are something that at all levels for stability. So it needs some correction. Now, to get the stability term right, which what Ralph argued is non-negligible, even in hurricanes, I was going to start this just assuming that it's neutral conditions, but Ralph Had some work where we found that there were cases where it wasn't. We had to also solve for similar profiles of potential temperature and moisture. So potential temperature is just temperature adjusted for the changes in temperature with pressure, with height. And it's very similar looking profiles. So we can solve for all these things simultaneously. And because L depends on the friction velocity, the analogous terms, and the temperature and humidity profiles, it's doable. So we end up solving for all these variables to get a wind at 10 meters. And one of the side results is we've solved for enough terms that we can calculate a stress, a sensible heat, and a latent heat, where it's just a product of these scaling terms, and then the density of the air, heat capacity, and a latent heat of vaporization for a latent heat flux. So it's just falls out. If you're going to do the work to get the winds right for calibrating a wind instrument, you're going to get the fluxes at the same time. And the technique we use when we're solving these is a conjugate gradient method, but it's very fast, very efficient, and it tends to be fairly accurate for the star terms, friction velocity, analogous terms. It's okay for the surface current probably. Stability is a little bit dicier, but it's not bad. But the roughness lengths are really bad. In a percentage sense, almost all, because this term is so tiny, almost all the air ends up going into roughness length. So I'm not going to show you roughness lengths because you don't want to see what we got. The profiles. Now, you think Dropsondes challenging to work with? You're right. We found that about 57% of the sondes couldn't be used for the ones we looked at from the NOAA flights. We only looked at NOAA flights and not Air Force flights. A small fraction of that was just because the instruments didn't work, which was a problem with some of the older instruments that were used well past their expiration date. And then a lot of them have gaps for unknown reasons. And that accounted for about half the failure cases. Other ones had clearly not profiles that were very different than what we expected. And when the winds decrease with height, it's kind of problematic. Maybe it's okay here. But these are also unfairly non-normal shapes. And we just threw them out. We could probably go back in hindsight and analyze more of these. But this is an example where there might be some big wind gust near the surface or a spray layer. And then some of these have very clearly, there's just no log layer in them that's evident. But a lot of them, over 40%, had log layers. And this is what you get where the scale on the bottom is wind speed, potential temperature, and humidity. And then in the vertical on all the plots, we have Z minus D, and it's on a log scale. So this should be linear in this coordinate system where we have a log layer. So it's fairly easy to plot things up like this, play around with different values of D, mainly from solving for it, and see whether it makes sense. And we can use this method to select the log layers. And we find that they're often not going down to the surface, as we would expect. So there's something else going on below that. And we can interpolate these to 10 meters and get a height. Now, when NOAA does that, they estimate over about 150 meters, take an average, scale it to the height of the lowest sonde, or the lowest sonde observation, do an adjustment to the surface, and get a 10-meter wind. So it's a pretty rough system. We're going to compare our results to theirs, so you'll see the WL150 down here in the corner. Our winds are over here. This is a fairly typical difference. It's not huge, which is nice to see. In this case, we had about a 4-meter displacement height, which is 4 meters higher than most people would assume it exists. And stability that's actually non-negligible. So it's an interesting example. And with the degrees of freedom we have, it's not really surprising that we're getting a good fit here. One of the things you'll notice is that there are twice as many wind observations as there are humidity and temperature observations. That's the way the system works. It would be nice to have more of both, but the sampling interval's a little different, for the response time. And if we look at this in a log coordinate system, then you can see the more typical log curves that people are used to seeing, where again, this is z minus d and 0 is d in this coordinate system. If you did it relative to the surface, then this would all be pushed up about 4 meters. So we see often this peak in this layer. And this is where things get to get interesting in new applications. This is an underwhelming example of how large this peak can be. It can be much larger, but it's typical of those conditions. The dots again are the layer heights where we have observations. In the profile for a potential temperature, in hurricanes, it's almost always almost isothermal. It's very well mixed. The moisture profile is usually not isothermal, but in these cases with very high winds and large displacement heights, it does tend to be quite iso, whatever it be for humidity, up through quite a high height, about up to the height of the displacement height. And this is not typical of other lower wind speed sondes. And these blue areas represent where the relative humidity is greater than 95%. So keep in mind it's fog is 100%, rain might be 85. So it's very, very moist here. There's a lot of spray. And it suggests that there is a spray layer below this log layer. And the spray is doing something here. So perhaps this burst in the speed is due to falling spray coming down with a higher momentum and causing this to have a peak down here. I can't prove that with this data, but that's consistent with what we're seeing. So when we solve for the profiles, again, we have one here. It's at very high wind speed, so the stress is 2 times the value you'd expect to see under a mid-latitude storm with 20 meter per second winds. It's not the stress, the friction velocity. The stress is 4 times as big. It's huge. And we can calculate drag coefficients that people would normally use or often use in models. Other models are based more off of the friction velocity terms. But these are about double what you'd expect, almost double for normal conditions. These are quite large as well. And you're getting a lot of momentum and moisture, temperature, energy being transferred. So it's possible fairly easily to take these sondes and do these things. But again, if you work with a definition of 10 meters above the ocean surface, you're going to get a much higher wind speed than you would expect from a log profile system. So it'd be interesting to try to do these with some of the high resolution remotely sensed winds from some of Paul Chain's flights as well, if he has data appropriate for that. One of the take-home lessons, the log layer does not extrapolate to the surface. It extrapolates to the top of the displacement height, which is often at higher winds a spray layer. So we have to exclude a lot of data from near the surface to get what we would normally consider a near-surface profile of winds. So that's a very different regime. How well do we do in comparison to NOAA? For low for a hurricane, which is not very low, there's a pretty good match. And keep in mind, these are conditions where your displacement height really is near 0, so it does make sense that there's a pretty good match. As the wind speed goes up, the variability goes up. Now, NOAA's algorithm was tuned with very different data long ago, and it didn't have a lot of data at these higher wind speeds when they did it. But if we look from 35 to 50 meters per second, we can see that there's an overestimate in the NOAA observations, which is consistent with what I've been saying about the 10-meter winds under those conditions being too large with us just 10 meters above the surface definition. And if you go to really high wind speeds, we see that there's a low bias in NOAA's technique for getting those winds. And again, the NOAA's technique was trained with very little data. They're two very different methods for getting winds. Having this much similarity is remarkable, even as it is. But it does suggest that there needs to be some retuning, particularly at the high end. A lot of caveats with this assessment. The conditions we're looking at where we can calculate log profiles are ideal for a WL150 method. So it's going to look relatively good. If we put in noisier profiles, we'll get worse fits. But we can't get our data to compare to under those conditions. We're defining U10 very differently with the displacement height. So there should be some differences, and they do show up. The scatterometers, we think about now translating this to measuring from space. Scatterometers or radiometers are going to measure a stress associated with waves. Scatterometers respond to ripples on wave surfaces, tiny short waves. Radiometers respond to white capping largely under these conditions, but it's happening at the surface. It's white capping due to waves. And if what we're seeing here is right, then the spray is extracting a fair bit of momentum, and scatterometers and radiometers are going to measure a stress associated with the ocean, which is great if you're an oceanographer. And they're going to underestimate the stress from the atmosphere, because the atmospheric stress is going to be this stress measured at the ocean surface plus the momentum extracted by the spray. And there's ongoing work with wave tanks by Trotsky et al. In Russia and other groups to estimate this spray. We're doing some of the work too on that. And the models do look like they're working well, but at these higher wind speeds, you see quite a difference between what you'd want for tuning an atmosphere versus tuning an ocean. So when we get to go to coupled modeling, this is going to be really exciting. I think these kind of solutions will be helpful. So let's look at transfer coefficients. I'll show you several of these, and I'll show you stresses and heat fluxes. And on this axis, we'll have the variable we're talking about, drag coefficient in this case. Have wind speeds on this axis. Our median solution is this line. The dashed line is plus or minus 2 standard deviations from that median. Standard deviations in the mean. And so it's a pretty wide spread. This line would represent the 25th percentile, 75th, 5th percentile, and 95th. And then in this light gray, we're saying we probably don't have enough data to be overly confident in the results. So for a drag coefficient, which is your friction velocity over your wind speed relative to the surface squared, we get this curve, and it drops off at high wind speeds, as people have suggested. But I say with caution that it drops off because this change is not real large compared to our error bars. It's probably happening, but we need to either work with more data or clean up the technique a bit, which I think we can do both, to reduce these error bars and then more confidently say with significant statistical significance that this is dropping off. Physically, it's very significant. So if you're calculating a stress, you would take this drag coefficient multiplied by the air density and the wind speed squared to get a stress. The roll-off out here again has been shown in several other analyses, and this gives you a little bit more feel about how uncertain some of that roll-off is. So let's compare it to past work. Again, the blue line is our result. The dashed lines are the plus or minus 2 standard deviations of the mean. The green line is work from Dave Richter, where he uses an ensemble of profiles, meshes them together at each wind speed to get a result. Mark Powell and his colleagues did the same work in the black line, and the white is from Haltusen, who did a similar approach. Now notice all these are lower than our mean, so that was concerning, but we do see a similar shape. Over here, we see large and pond in the red, pushed beyond probably reasonable limits, and Smith et al. Definitely pushed beyond reasonable limits. And we see, though, down at the wind speeds where these are good, I mean, there's enough data to say, hey, you know, they're in the ballpark. We're getting a really good match to these. And these other models are underestimating over there. So it's very encouraging to see that we're matching conditions, which in situ data has shown us are, you know, reasonable with a fair bit of spread that's not shown on here. Again, the key difference between the techniques, we're working with single profiles. They're applying a log method with slightly different parameterization into the whole profile. They also, in those studies, looked at the drag coefficient again as a function of the location in the storm. So this is the direction of the storm. This would be your left front sector, right front sector, rear sector. And they separated the drag results by these different sectors, and they're colored roughly analogously over here. And you can see you have lower stress in this, or lower drag in this region's, higher drag here. And this looks disturbingly like a lot of the spread we're seeing. So I'm not going to claim that all our spread is due to this geophysical process. It's certainly, there's a lot of noise in it as well, but it probably is contributing to the spread. And if we had more data, we could do a similar study. We don't. We need to process a lot more data to be able to do this kind of study. But it's interesting to use this just as to see the natural variability is so large when you take into account all the different sectors. So if we look at stress, we can hear stress on this axis is a function of wind speed. We can see that stress goes up, and then it starts to level off around 55-ish meters per second. But again, this leveling off is much smaller than our error bars. So take it with caution. If instead we look at sensible heat, so this is heat transferred as thermal energy, but not through phase changes, we see a heat flux that goes up with increasing wind speed, much like we'd expect, until, oh wait, 40 meters per second. Then it goes down. Well, how can this happen? The spray is coming into play around here. And it looks like when we get enough spray that the top of the spray is cooling. So it can't cool down below because it's saturated environment, and it can't cool through evaporation. But at the top of the spray layer, it can cool. And we see in the profiles the cooling at the top of the layer, so it makes it consistent. And you get a reduction in the heat flux because the apparent ocean surface, which is the top of the spray layer and not the ocean surface, is cooler than it was, and it starts to reduce the sensible heat flux. So that way of powering storms decreases as we get into this higher wind speed range. That's really exciting. So again, the evaporation, and again, cautiously stated, I'm uncomfortable saying it goes negative because of the large error bars. It goes near zero would be a safer statement at high enough wind speeds. And most of it's driven by latent heat flux. This is contrary to some new modeling results where they get, some Korean colleagues get very good model results when they have high sensible heat fluxes. So we're looking into this more. It's an interesting comparison. If we look at latent heat fluxes, again, latent heat flux on this axis, wind speed here, and we see it go up, and at about the same time it curves down. And a lot of this drop in curvature is because we saw the curvature in the stress dropping off. This term is dominating it, but there are also some changes in the Q star and theta star terms. So this is playing the biggest role here in that. Now, hurricanes are powered by a ratio of the drag coefficient or the enthalpy flux to the drag, and you can so looking at how these are ratioed to each other is one of the things we want to do down the road. So in conclusion, did we gain useful insights into the boundary layer of tropical cyclones? Sure. We identified rolls of spray. We identified rolls of displacement height. We showed that you can get these from single sondes. It's pretty neat. Did we improve our estimates of 10-meter winds? On the basis of physics, better physics, we could argue that we've improved it. Have we demonstrated that it's better? That's going to take a lot more observations to demonstrate that. But in terms of physical parameterization, absolutely it's better. But it's neat that the NOAA result actually works so well for lower wind speeds. And as others like Federica Polveri and Paul Chang, Saran Yelnök have shown, it doesn't work. At the higher wind speeds, we see the same thing. Caveat here, of course, we can't do this for all dropsonde profiles. And a lot of the reasons we can't is because the log layer is too thin in terms of observations. We need a certain number of observations given all these free parameters. And to those people designing dropsondes or similar instruments, we'd really like to see more frequent sampling or a slower fall rate, something that gets us more data density in the boundary layer. Were we able to calculate fluxes? Sure. Very noisy fluxes could be calculated. But we have enough of them, you can start to see patterns of behavior. We need perhaps 3 times as much to get the error bars down to the stage where we could really more confidently make conclusions. So we've got to increase the size of the data set. We can do that. There's observations from the Air Force as well as NOAA. We can't go too much further back in time because the sampling rate drops off. We can develop more automated techniques to find these log layers. We haven't yet, but that's something we really need to do. In our solving code, we can introduce some constraints that improve the roughness lengths, which would reduce some of the noise, because we know that some of our bad answers are associated with bad roughness lengths. And ideally, there would be groups that would either upgrade sensors or work with something that could somehow survive in the boundary layer and move up and down through it, although I think that's awfully optimistic. But we just need more data per unit height and more data in general. And to understand and apply these things better, we want to look at the roles of spray. We want to look at these ratios that are really important to hurricane evolution. One of the things you can do with this is look at salt mass fluxes and the transport of salt into the atmosphere. We could try to work in a sea state dependency, if there is one. That's highly debatable, but it does influence spray production apparently, and that it could be important there, and that could account for some of the diversity in the boundary layer characteristics that we're seeing. And then once we get comfortable enough, this does probably set up the route for improving calibrations from aircraft. And then if you could get satellites that would see through the rain and well enough, you could try to then work on the calibration to the satellites. But this is I think a step-by-step process to understand what you're sensing and calibrate the aircraft to it, then move up to satellite. Thank you very much.
Thank you, Mark, for the very interesting and informative presentation. The floor is open for questions. Feel free to unmute and ask your question or put in the chat.
Yeah, Tony, I have a question.
Go ahead, Marcos.
Yes, thanks, Mark. Very nice presentation. I just have maybe a conceptual question, yeah, because you try to select those dropsondes which are, let's say, reasonable from the, let's say, lock type of behavior, and then with that, you try to, let's say, get to U star, and actually you do the right thing to use actually the three fluxes, turbulent fluxes, and derive all the parameters at the same time, which is something I like. But then if we think about wind stress, right, it's about molecules, no, that are hitting the surface. So you say, okay, we have a layer between, let's say, 10 and 30, 40 meters, which should be low profile. But doesn't it matter what happens beneath 10 meters? Yeah, because you're talking about the spray layer. And if we want to get the wind stress right, we should look at the spray layer, I would say, right?
Yes and no. So we do definitely need to look at the spray layer if we're going to get the ocean stress right from these observations. It makes sense that the log profile layer is above the spray layer, and the stress is not just hitting the surface. It's really a perturbation in a U component or V component and a W component of winds. So you don't need a surface for that. To actually affect the ocean, it has to hit the surface. So for an ocean stress, you would think then that any modification due to the spray has to be taken into account. And I agree. This is actually getting an atmospheric stress. It is not getting the stress on the ocean. The ocean stress will be reduced if there is a substantial spray layer. So we would be overestimating the stress on the ocean, and those heat fluxes are going to be modified as well from an ocean perspective. This is very much an atmospheric perspective.
Yeah.
So yeah, we do need to account for that, and that's going to take probably a lot more modeling and verification of the characteristics we see of spray. So there are models where we can calculate the distribution of spray, but then there are others where there's evaporation and other stuff taken into account. I'm not an expert on that, and I see some divergence though in the little bits I do see.
Yeah.
But so that's ongoing work.
So another point here, I guess, is that we've been arguing that we get these strong decelerations when you get close to the surface. Now you see that in the spray layer, it looks like you have a different behavior. But I think the point remains, which is the fact whether the dropsondes are able really can we really use them as a proxy for wind close to the surface, because they're falling pretty fast. We know we have height assignment errors. We have the problem of the sampling frequency. So getting, of course, information close to the surface is going to be uncertain. And you're using, of course, in the spray layer, it's very sensitive, I guess, the information that you get there close to your displacement height, let's say. And we know at least that we have suspicions that these winds could be biased just because of this reason. And I guess this question remains there. So this is sort of embedded in your algorithm. You cannot really resolve or discern from that, right?
Right. There's good reason. If there's a big jump in speed, the dropsonde will have issues with it. I mean, it should be possible. Somebody was pointing out you just hang one of these things in a wind tunnel and turn the winds on and off, and you could actually find out what the response rate is from a dropsonde. And it'd be really nice to know that number, and that would be a better way of addressing it than this. The sonde values in that layer are suspicious unless you can convince somebody that it samples fast enough. I agree. But this particular method of getting the atmospheric component doesn't rely on those data. So we can get rid of all those from the question, because the physics we're trying to model don't work in that layer. If we try to include data from that layer, we're going to get really bad results. These log layer analyses are very, very sensitive to taking data from outside a log layer.
No. Thanks.
Thank you.
Any other questions, Mark?
We'll further discuss this at the IOEWST.
Yes.
Ben, go ahead, and then Sarah.
Oh, hi, Mark. Thanks for the talk. I really enjoyed it. So I have a question. So, you know, the log law doesn't work when the flux is not constant. And spray can cause that because you have these sort of sources and sinks of spray evaporating or warming the air. Um, it's been sort of kind of hypothesized that the spray layer thickness is a nominally one significant wave height. I'm wondering if you have seen in your analysis of the dropsondes any indication for what the thickness of that layer might be based on the way the fluxes are becoming not constant, or based on anything else.
I can't do it based on them becoming non-constant because that'd be a spatial derivative, and we don't have that kind of data. The sampling is too sparse for that from SONS. It's a good question. So Jim Edson's looked into that for ships sailing through fronts, and he's found that the basic flux parameterization seemed to work okay. The eddy covariance data match the data from the bulk formula fairly well. For terms to the thickness of the spray layer, we haven't tried to pin that down well enough yet. That's an ongoing question. It does look like it's beyond a significant wave height. I'd have to get estimates of the significant wave heights from other parts of the aircraft data. I don't have it all yet. It's not always available. In many of these flights, it wasn't available. So it's not a simple question. It's a good question, but it's not one I can well address.
Right. Thanks. I appreciate that. Yeah, that sort of thickness is like a pretty important thing for a lot of the spray parameterizations.
Yep.
So yeah, appreciate it.
Sarah?
Yeah, Mark, really interesting. I wondered, you showed this drop in heat flux when the winds are really, really high. Does that imply that the maximum air-sea heat flux is happening outside of the peak of the winds on the periphery of the storm?
Well, for most storms, this would be more like a peak wind. But for those really extreme winds, if we believe the drop, it does suggest that. But keep in mind that in terms of forcing, a lot of it is the ratio of this to a drag coefficient, because the drag is also dropping. So it even though it's a drop in energy input, there's a drop in the energy extraction as well, and that's why we want to look into the ratios and see how that comes into play. It's a really neat question because it doesn't look like it behaves quite like we'd expect. Normally, you would expect this energy to just keep going up and up, and it might given these air bars, but if you follow this mean, it's suggesting that there's something else going on that's changing the system, and it might be another feedback aspect into controlling the strength of the storms, or if you say that spray is impacted by water temperature, there could be connections there as well that would be really interesting to start tying into some of these studies.
Yeah.
Mark, I have a question. What is the humidity height under such condition? The height of the spray layer or above the spray layer?
Okay, so I have an example for that. This is a fairly reasonable example for that. So in the spray layer, it tends to be the same value of specific humidity. It's also near 100% saturation, so it's the same relative humidity, but the specific humidity is what you're interested in. And then above the spray layer, it starts dropping fairly quickly. And keep in mind, this is the spray layer in terms of impacting things. There's spray at much higher heights. A little bit above the spray layer, you start to see that logarithmic profile, but not right above it. There's a transition between this ISO specific humidity layer and the log layer. And it's not a sharp transition. Does that answer your question?
Yeah, so I'm thinking that if there is a kind of high resolution weather model that give you hurricane condition fluxes, I know they're not reliable, but let's say that they give you some estimate. How would they, in that model, what height, humidity at what height would they take? Something like that, or if they kind of represent the spray layer? I know they don't, but
Right. So we found that it was pretty variable, the height of the spray layer.
mhm,
So I don't have a good answer for that because of that variability. And if it's due to different sectors of the storm, maybe we could give a more concrete answer. But we don't have
mhm,
enough data to confidently do the different sectors. But it is suggesting that those sectors do play a role in this because it should have a large impact on the spray. Um,
mhm.
and I think you're on the right track for trying to do a simple fix, but it's not clear yet what that answer would be. Again, I think I need 3 to about 9 times as much data to answer that question.
Mhm. Yeah, the same question applies for air temperature or delta T. At what height should one look at the air temperature?
Yeah,
Uh,
and it's a really good question because you can say the same for any of these variables. And we initially started assuming that they could all have different displacement heights.
mhm,
And we found that they were all really similar when we did the analyses. So whatever the answer is for one is going to give you help give you an answer for the others. So
mhm,
if you have the displacement height, you have your log layer, it's going to come and it's going to extrapolate to something pretty far away from it at the displacement height. So you want to
mhm,
be maybe 1.5 times the displacement height, whatever it is.
mhm,
So if we could start figuring out what this displacement height is, then that would help you get the height of the layer where you'd want to look at it.
mhm.
When I was doing wave tank work, 1.5-ish was a cautious estimate for throwing out everything that wasn't going to fit a profile.
Thank you. Anyone else has question for Mark? So I have one more question, Mark. I know it's not part of your talk, but I think you're very knowledgeable on this. Uh, how reliable is eddy covariance flux estimates under hurricane conditions, assuming that the buoy or doesn't topple or anything?
Well, okay, so that's a great question, and I can get in all kinds of trouble answering it. If we look at, say, stress, I'm trying to get to the stress slide. If you have conditions where you don't have too much spray modifying things, it's probably, if you properly monitor the motion of the buoy and account for that in the calculations, it's probably pretty darn good. But once you get a displacement height that gets to be less than 2/3 or more than 2/3 of the height of the sensor on the buoy, you're
Mhm,
not really taking observations from a log layer.
mhm,
And that's a fundamental assumption for doing those calculations. So
mhm,
under those conditions, I'd get nervous. So NOAA flies aircraft, used to fly aircraft,
mhm,
and floats low and measure fluxes. I don't think they're allowed to anymore. And those would have been great for the atmosphere. But again, with the spray layer modifying stuff, it's not going to give you a stress felt by the ocean. So the eddy covariance flux should be measured in a layer where you have a log layer.
mhm,
And in the cases where the sea state is such that you don't get much of a spray layer, it might be good.
mhm.
In the cases where you get a large thick spray layer, it doesn't make sense to use it to me. Jim Edson could probably give a much more accurate assessment, but that would be my impression just based on um, applying it to the conditions which it's meant to model.
Got it. Thanks. Look.
Yeah, I was going to bounce on that. I mean, this should be a topic of an entire talk because this is trivial. The thing that I wanted to add is even if you're motion compensating, correctly your observation to do a decorrelation flux in this kind of environment, you're no longer in a reference frame relative to mean sea level. The fact that you're moving up and down with significant height is a big deal, which means that you have to interpret your fluxes, your stress differently. And Tetsuhara had some paper on that. Peter had some paper on this. We poked around at this as well. It's not that you can't do it. It's just you have to interpret it in different fashion. You have to be a little careful. These are very difficult observations, especially in hurricane conditions. The kind of drag coefficient and stress that you're showing and the range of it shows that we still have a lot to learn. Because the way we're parameterizing things are convenient, like the drag coefficient, because we can plug this in models, but clearly they're not the best based on the scatter.
Yeah. So then, to take this further, if we could get enough observations near the surface and enough observations above, you could really start looking at how much momentum is being pulled up by spray.
Yeah. Yeah, and it's super interesting, and I'm very interested in this. That's why I get excited about those kind of things. But there's a lot of unknown. Looking at the spray, like generation layer, for example, how high does it extend? It's still like very much hand waving, and it's just really hard to get those kind of data. And there is a lot of challenges with Dropsondes, as wonderful as they are.
Yes.
So.
No, and Dropsonde, there's a bunch of new instrumentation coming out that might prove alternatives to the Dropsonde as well, but those are still under development. And I don't want to speak too much to that, and I don't think the sampling rate's that much better.
Yeah, but there is, going back to my point is that you can use eddy correlation, eddy fluxes in those kind of conditions. You just have to interpret them differently. And just because of the reference frame, you're in the reference frame of the moving surface.
Yeah, you're right, because you're going to get a U prime W prime or B prime W prime regardless.
Yeah, thanks, Luke. Any further questions? Okay, if not, many thanks to Mark again for the interesting seminar. Appreciate it.
Inviting me.
Take care, everyone. Bye-bye.
Thank you. Really great. Bye.